Okay, so now we show that the second statement implies the third. So suppose that there exists a surjection, which we'll call F, mapping the finite subset of consecutive positive integers from 1 to n into the set B. Define a function g mapping the set B into this finite subset of consecutive positive integers by g of B is the least or smallest element in the fiber of that element B. Now, since the function f is surjective, we have that for every element B in the set B, the fiber of that element is not empty. Now, if the element B is not equal to an element B prime, then the intersection of the fiber for the element B with the fiber for the element B prime is empty. That is, they have no points in common. And so the least element in these fibers are not equal. That is, g of B is not equal to g of B prime, and hence the function g, which is a map from the set B into the finite subset of consecutive positive integers from 1 to n, is an injection. Okay, so now we prove that the third statement implies the first. So suppose that there exists a surjection, an injection G from the set B into a finite subset of consecutive positive integers from 1 to n. Now, if G is surjective, then this function is a bijection, and hence set B is finite. Otherwise, there exists a superset A which contains the set B, for which we can form a bijection, which we'll call F, mapping the complement of the set B in A onto those elements in the finite subset of the positive integers from 1 to n that were not mapped onto by the function g. Then the function h, which is a map from the entire set A into the terminating subset of positive integers, consecutive positive integers from 1 to n, defined by h of A is the same as g of A for those elements that are in the set B, and f of A for those elements that are in the complement of B in the set A. this function is a bijection. And so the function, the set A is finite, and since B is a subset of A, set B is finite. Okay, so this theorem has a corollary. Finite unions of finite sets are finite. So proof. First, we show that if the sets A and B are finite, then so is the union of A and B. Now if either the set A or the set B is empty, the result is trivial to show. Otherwise, neither A nor B are empty, and there exist bijections, which we'll call F, mapping set A into a terminating subset of positive integers from 1 to m, and G, mapping set B into a terminating subset of positive integers from 1 to n for some positive integers m and n. So define a function h mapping the terminating subset of positive integers beginning with 1 and ending with m plus n into the union of A and B by h of I is f of I for I ranging between 1 and m, and is g of m, I minus m for values from m plus 1, I ranging from m plus 1 to m plus n. Now notice that the function h is a bijection if A and B have no elements in common, and if A and B do have at least one element in common, then the function h is surjective but not injective. In either case, the function h, which is a map from a finite set of positive integers, consecutive positive integers from 1 to m plus n into the union of A and B, is a surjection. And so by the previous theorem, the union of A and B is finite. So now suppose that the sets A sub 1 through A sub n are finite. Then clearly A sub 1 is finite. Now assume that the finite union from I equals 1 to n minus 1 of A sub I is finite. Then the union from I equals 1 to n of A sub I is the union of two sets. The union from I equals 1 to n minus 1 of A sub I with the set A sub n, which is the union of two finite sets, and therefore is finite, once again, as it is a union of two finite sets, and hence, by induction, finite unions of finite sets are finite. So as an exercise, let tau be the set of all subsets of a set X, where that subset is either the empty set or the complement of that set is finite. Then show that the collection tau is a topology on the set X. Alright, so now we'll look at the exercises from the previous lecture. And the first we'll state as a theorem. So let Y be a subset of the poset X with the relation R. Then the supremum of Y is unique when it exists, and the infimum of Y is unique when it exists. So proof. First statement. Suppose that Y is bounded above and let the set U be the set of all upper bounds of Y if the poset U with the relation R has a least element, then that element is unique, and hence the supremum of Y, which is the least element in the set of all upper bounds, is unique. Now if the poset consisting of all upper bounds with relation R has no least element, then the supremum of y does not exist, and if y is not bounded above, then we write that the supremum of y is positive infinity, which is another way of stating that the supremum does not exist. So second statement, suppose that y is bounded below and let the set L be the set of all lower bounds of y if the poset consisting of the set L together with the relation R has a greatest element then it is unique and hence the infimum of y, which is the greatest element in the set of all lower bounds, is unique. Now if the poset consisting of the set of all lower bounds of y with the relation R has no greatest element, then the infimum of y does not exist, and if the set y is not bounded below, then we write that the infimum of y is negative infinity, which is another way of stating that the infimum does not exist. So notice that it is not true that every set that is bounded above has a least upper bound and it is not true that every set that is bounded below has a greatest lower bound. Okay, so as an example for the exercise from the previous lecture, let script B be the set of all half-open intervals of the form A inclusive to B of the reals with all half-open intervals of the form A to B inclusive of B of the reals. Let A, B, and C be real numbers such that A is less than B, which is less than C. Notice that the singleton containing the set B is the intersection of two basic open sets, and therefore is open. So every subset U of R is a union of singleton sets, and is therefore open. And since every subset of the reals is open, this is the topology generated by the collection script B is the discrete topology on the reals. Okay, so we'll end here for today. Next time we will continue to look at countable sets, including countably infinite sets. So I hope you have enjoyed the 11th lecture. Thanks for watching.